video is a video about intuition. I would like you to develop a little bit of understanding about why we're going to be doing what we're going to be doing when we're solving linear systems of ODEs. So it's going to be a way more hand-wavy than we usually do, but I really urge you to pay attention, because giving an understanding of what we're doing will give you a nudge to actually solve problems. So we're looking at homogeneous systems of ODEs with constant coefficients. So we have x prime equal ax, where this time a does not depend on t at all. So x is a vector of unknown functions depending on t, and a is just a matrix of real values. Our first step that we have always done when we don't know how to solve an ODE is find for equilibrium. So we have to find the solution of ax equal to 0. Trivially, that means x is equal to 0. Here we're assuming the determinant of a to be different than 0, so x equal to 0 is the only solution of our system. And the fact that the determinant of a is different than 0 will make it easier in the other situations. But the first step is that if you have a linear system of ODEs with constant coefficient and it's homogeneous, 0, the vector of zeros, is the only equilibrium that you have. Now that we have that, let's think a little bit of the matrix A as a transformation. On one hand, we have Rn with a vector x in there, and A transformed this vector x in a new vector, the vector Ax. But Ax, we just said, is the derivative of x. So if you're thinking of x as a vector that changes over time, as we want to think about it, because x is indeed a vector, so we can think of either the full arrow going from 0 to a point, or the point itself. Now that we have computed Ax, we know how this arrow is changing over time. It's changing towards Ax. So that is x prime. Remark that Ax is always different than 0 if x is different than 0. So x is always moving around in some directions or other. And the direction in which x is moving towards is determined by Ax. Let's have a sidestep and remind ourselves about eigenvalues and eigenvectors. If you're taking a transformation a matrix that goes from Rn to Rn, an eigenvector is such that A only stretches or squeezes it, but keeps it in the same direction. That means that when we're thinking about a linear ODE system, what we're thinking about is V1 being stretched, being displaced by AV1, that is in the same direction as V1, because V1 is an eigenvector, and V2 having a derivative that is AV2 that is in the same direction as V2. So the first intuition is that eigenvectors move in a straight line. If you start on an eigenvector, the transformation A is just stretching you or squeezing you, but it's always in the same direction. So when you're looking at the ODE system, x prime equals Ax, and you're starting on this line, you're going to stay there. The same goes for AV2, and every other eigenvector stays in there. The second intuition is that the speed at which you're moving depends on the eigenvalue. Remember that if V1 is an eigenvector, AV1 is equal to the eigenvalue associated to V1 times V1. So you can go very fast if your eigenvalue is big, or fairly slowly if your eigenvalue is small. You can often go backwards if your eigenvalue is negative. So what happened to the other points? The vectors that are on eigenvectors, multiples of eigenvectors, are moved by your system depending on the eigenvalues. The points outside of that can be considered as combinations of the two eigenvectors. So if you have a point x, a vector x, that can be written as a sum of a component in V1 and a component in V2. And those two components, we know how they work. The component of x along V1, that is going to behave as V1, while the component of x along V2 is going to behave like V2. This is why when we talk about linear systems, it's really important, because we can break x into two parts, and if we know what happens to the two parts, we know what happens to x. That is the principle of superposition that we have seen. So the third intuition is that x moves like the sum of its components.